Recording in progress.
Good morning, everyone, and welcome to the second week of this class. We completed chapter 17. Today is chapter 18. Actually, we're going to start a new topic. And before I do that, I know I sent a survey on Sunday, and I was hoping to get as many feedback as possible from you guys. It was not a required survey. I had 7 replies. Because the survey was anonymous, I couldn't really honestly tell if all of the 7 replies are coming from 7 different people or is just from basically different groups of people. But it doesn't matter. I get basically the main points from the survey is the fact that so far, at least the respondents, were happy with the pace that we're going with. This may change down the road, so we will gauge this one down the road too. Also, there was no recommendations in terms of making things a little different to see if we can make it. So basically, this is the pace. On Tuesday, we're going to meet to introduce the topics. On Thursday, we will do applications and finish basically the topic of that week, and also do the lab. So that's basically how this Tuesday, Thursday, this is how the course is going. There is assignments also on mastering physics that hopefully you guys are taking care of. I will monitor that from time to time. In terms of the first participation assignment, with the exception of 3 people, everybody basically responded to it, and that's good. So the other 3 people, please do reply to those prompts. That's a requirement. So it's not really an option for the discussion for week 1. And then also don't forget that you have a quiz from chapter 17 that you have to complete. And also you have a lab. So there was already 3 assignments as of the first week, in addition to the homework. So there is quite a bit of work that needs to be done. Do not delay things. Do not look at the deadline or the due date, I should say, and say, this is the time when I'm going to start working on that assignment, because some of them are time consuming. So you really have to start as soon as possible on these assignments. So this is in terms of the survey. The other thing also that I wanted to know from the survey is the feedback on the Gaussian. I mean, honestly, from all of my classes, doesn't matter which class I'm teaching, I rarely rely on what you guys have seen before, whether in math or physics. So I try to cover the concepts, try to explain them, try to go with examples. And of course, I hope that you guys will look at different resources to strengthen your grip over those concepts, okay? The Gaussian integral is needed for this part, for chapter 18 actually, and also down the road when we get into quantum mechanics. So it's really an important concept. It is so important that probably in physics and chemistry, there should be a whole chapter dedicated just on it because of its importance, okay? So I will try to tackle it from different perspectives, from a purely numerical perspective, namely using software to calculate those integrals, and also we'll go through the analytical method, basically going through it. And so that's basically in terms of the survey. The survey is now is done, so we really don't need you. I don't need you guys to fill it after today. But as I was saying, there will be more surveys down the road. Chapter 17 really dealt with the concept of temperature. The zeroth law was simply to introduce a thermometer, and the whole chapter dealt with the temperature. If I increase the temperature of a substance, how is it going to basically how is it going to behave? I mean, it's going to expand. So we looked at the linear expansion and the volume expansion. The lab this week, this Thursday, is going to be on this topic. So we're going to get a little bit more detail about that. And also, it dealt with the heat transfer that is a concept that is really related to the temperature, whether through convection, when there is a difference in temperature and the density gradient, and also for the emission of radiation, namely through when you have a body at a given temperature. This is called the black body radiation. We're going to come back to this topic later on down the road also. And that is the T to the power 4 law. And then Stefan Boltzmann law. And then we dealt also with the transfer of heat through media. Okay, that is the heat current again, and how is it related to the gradient of temperature delta T. So it's the whole chapter 17 dealt with this concept. And note that the chapter 17 dealt from it from macroscopic perspective. We really did not know or have no clue what temperature is, other than the fact that we have a thermometer that can measure it. And we can assume that the thermometer is as accurate as it can be. Chapter 18, though, is going to delve a little bit more and try to understand what that macroscopic phenomenon is. What is that temperature, okay, from a microscopic perspective, from deep inside. The debate was in the mid-1800s about the nature of temperature and the nature of thermodynamics in general and the nature of heat in general. And there were two schools of thoughts. There were two basically groups of people, scientists. Those who believed that the nature is energetic in nature, and as a fundamental concept, it's related to energy and how energy is distributed in systems. And the experiment of Joule, of course, proved that. There's no question about that. So it's energy, okay, whether temperature or heat and all of these things. There was another group of people that started to become louder and louder, and that is the essence of it is that there is a fundamental nature to matter, namely that air, as we look at it, it's not empty. There are particles in it, atoms in it, molecules in it, okay? That group of people, the atomic basically theory people, they were kind of few, and they felt a lot of pressure from the first ones because it's very easy to calculate energies, to measure energies, to measure temperatures with thermometers. But these things we don't see, they probably don't exist. So that's basically how the debate went out. There was two scientists, namely a German by the name of Clausius, who did a lot of work along this atomic theory, but he did not have a lot of basically experimental data to back up his work. When his work was translated to English from German by Guthrie, later on Maxwell, who was working on the theory of electricity and magnetism, you know, Maxwell's equations that you guys had in physics too, he started to build this theory of statistics of these particles, okay? And this is really the topic of today, okay? So this is basically the topic from chapter 18. Obviously, his work later on was taken to Germany and looked at by Boltzmann, who was actually a grad student at the time, and he did not have any mastery whatsoever of the English language, so he really struggled through the publications and tried to understand them, and he had actually a dictionary trying to read the English publication of Mr. Maxwell, and then he worked his way through it, and he came up with a very, very solid interpretation of the laws of thermodynamics using this particle theory. One of the younger people at that time was Mr. Max Planck, who took the step further, and he was kind of fuzzy a little bit, honestly, on the particle nature of matter, whether or not atoms exist or not. And he took that step further, and the debate raged on. And Mr. Boltzmann was really on the forefront of the debate. He believed in the particular nature of matter, that there are atoms in the air, there are molecules in the air. That is really where the temperature and heat and everything else is coming. Of course, there was a lot of critics at that time to him, and that led to his demise at the end. Basically, he committed suicide. I don't know, honestly, if it's probably he had issues before or not, but at the end, the depression took the best of him and he committed suicide. The point being is, this was a story that evolved, and today is the topic of chapter 18 that deals with right in the middle of that debate. Okay, so let me share with you the screen. We have quite a few people who are not here. I know we have 2 people, 1 person, I guess. Okay, or 2 people. I'm not sure exactly, but we'll take the attendance later on. Okay, so let me share with you the screen. So the question is, phenomenologically, basically from phenomenon perspective we knew about this law. The pressure times the volume of a gas, which are called ideal gases because they satisfy certain conditions in terms of low density, in terms of, they're all typically the same thing. It doesn't matter what the nature of the gas is. It could be oxygen, it could be nitrogen, it could be whatever you can think of. As long as the density meets certain requirements, they are so-called ideal gases. Okay, well, ideal gases satisfy this law that you probably have seen it in chemistry. Okay, the pressure, this is the volume of the gas, this is the number of moles, it's just a number. This is the temperature in Kelvin. By the way, you really need to be writing these things, okay? You may write it in your own notes, you may write it in your own things, but you really need to write this, otherwise you're going to have difficulty following. So in Kelvin, not in Celsius, not in centigrade, not in Fahrenheit, not in, what is the other one? Rankine. The only unit that is acceptable in here is in Kelvin in this expression. Otherwise, when T is equal to 0, you have a problem in here, okay? And R is a constant. R is 8.314. Okay, the units. Let's talk about the units, okay? It's important to master the units. The pressure, if you guys remember from your physics 1 class, is just a force over area. And the force is basically a kilogram meter per second squared. Newton. I know it's a Newton, but I'm writing it in MKSA. It's a meter, kilogram, and second squared. And the area is a meter squared. Okay? So in the units for pressure, it's the same thing as a kilogram per meter second squared. That's it. I mean, I know you guys use the Pascal. That is true also. That is in honor of Mr. Pascal, who basically did a lot of work on pressure. So that is the pressure. Now, if one of the problems tell you the pressure is 1 atmosphere, and you will have that. If the pressure is 1 atm, atmospheric pressure, that means it's 1.01 times 10 to the power 5 Pascal. And Pascal is as good as any of this fundamental unit, just as the Newton is good to represent this unit. Okay, same thing. They are not fundamental units, but they are SI units. They are basically part of the metric system. Okay, derived units. So this is one conversion that you have to be aware of. Now, times the volume cubed. I mean, times the volume, which is in the meter cubed. So again, the volume is simply distance cubed. That's it. So if I take the pressure times the volume, note that the pressure I always write it with a lower p. Okay. This has the same units as kilogram divided by meter second squared times meter cubed. Cancel the cube with the meter, and you will end up with the kilogram times meter squared over second squared. And this is energy. I mean, if you're not convinced, this is a force. This is a force in Newton times meter. So this is a Newton, and this is meter, and this whole thing is just in joules. Again, it's not a fundamental unit, the joule. It's a derived unit in honor of Mr. Joule, just to basically that he worked on this thing. So we gave the joule as a kilogram meter squared second squared. So this is actually an energy. Okay. So the first part in here in my units for R, this side in here is in joules. So it's in joules divided by the units for N. N is a number. N is a number. But because it's written this way, that number represents the number of moles. So we call it mole. Not that the mole is a fundamental unit, but just to represent that we're talking in terms of number of moles. How many moles are we talking about? 1, 2, 3, 4, 5, or 0.5 moles, or half a mole, or something like that. Remember, a mole is an Avogadro number of that substance. 6.022 times 10 to the power 23 of that substance. I hope that you guys, is this some sort of a refresher for some of you, or at least most of you? Does this sound familiar?
Yes.
Yeah.
Okay.
Yeah, it does.
So, okay, very good. So I'm glad that for some of you, this is rings a bell. If not, please let me know, and I'll be more than happy to talk about this one in here. So the last unit in here is the unit of temperature. So I'm looking at the unit of R. Okay, this is a constant. Okay, and this constant, as I was saying, has the units of PV, and PV is in joules. It's kilogram meter squared divided by second squared. This is a number, just like any number that you meet in the street, okay? This is T, and this T, as I was saying, is in Kelvin. So that fixes the units for R. In SI, okay? In the metric system, le système international. So that is the unit for R, okay? So we have everything. So this experiments, this law, basically, think about it this way. Fix temperature and increase the pressure. If you increase the pressure, the volume decreases. Or decrease the volume, the pressure increases. As long as the temperature is fixed, as long as your whole apparatus is sitting in some sort of a heat bath or a temperature sink, okay? So that it doesn't change. Now, it can fix the volume, take a container and seal it all the way through. So the volume is fixed, and raise the temperature. Put it under like what you do with the pressure cooker. You seal it and you put it under a heat source. Okay. So in this case, the temperature increases, the pressure increases. If you open it a little, and you see the pressure going up. Actually, you can measure the pressure. So P and T are proportional to one another. The same thing. If you keep the pressure constant and let the volume expand like a piston, it goes up and down. As the temperature increases, since the pressure is fixed, the volume increases. The piston goes up. If you decrease the temperature, the volume shrinks. Okay? So V and T are proportional as long as P is fixed. And you can play with these things. You can move. So this law was known under different names until it was put together and was called the ideal gas law. Okay, so I know that you probably spend a lot of time in chemistry just deriving this expression. So this is an experimental law. Where this T is what your thermometer from chapter 17 tells you it is. This P is measurable with pressure gauge. This volume V is measured with, take whatever container and put it in and do an experiment with it, or you can measure the volume using the old-fashioned way, calculus or whatever method you have. N is a fixed amount of matter that you plug in. Okay, how many moles you're going to put in. R is a constant. R, if you repeat this experiment over different substances and you do the ratios, you're going to find the same ratio here no matter what. PV over NT is always fixed number. That doesn't change, 8.314. So this is a known law. So let's try to understand it from a microscopic perspective, from the story that I was telling you about in the beginning, when Mr. Clausius, followed by Mr. Maxwell, James Clerk Maxwell, and also the work of Mr. Boltzmann, add to them Mr. Planck and everybody else, Gibbs also was involved. All kinds of physicists and scientists were involved in it. Here is the model that we're emerging with. In this room where you are right now, if you look around you, there is something that you don't see, but the air where you are is filled with particles, okay, molecules, okay? These particles, I'm going to assume that they are rigid, small, actually so small that if you take them and clamp them together, their volume is very small compared to the room where they are, okay? So if you take all of these molecules and pack them together one next to one another, they will occupy a very tiny volume from the room where they are right now, okay? And when they collide, their collisions are elastic collisions. Remember, elastic collisions conserve two quantities. The momentum is conserved. The momentum is always conserved as long as there are no external forces. Plus, actually, the kinetic energy is also conserved. Okay, conserved. Okay, so that's what I meant by them being very tiny. Their density is so low. That means this definition, ideal gases. Okay, and I'm going to assume that they are all the same. Okay, uniform. It doesn't have to be same mass. Like, for example, this room, now we know that it's, what is it, 78% nitrogen and 21% oxygen and negligible fraction of all of the other gases, carbon dioxide and water vapor and all of the other things. So it's mainly nitrogen, okay? So we're gonna assume that it's mainly uniform stuff, okay? This theory really doesn't care that much about this last point. And just for my summations later on, it's easier to take the mass out of the sum. What else do we need to make about these things in here? Okay, I think it's enough for right now. So we want to understand how we can get pressure out of this molecules in the room where we are right now. Okay, right now the temperature, I don't know exactly how much the temperature is in your place, but the temperature, I would say probably 20-25 degrees Celsius, okay, about 300 Kelvin. So temperature is about 300 Kelvin, maybe less, okay? If you look at it, maybe it's around 290 Kelvin, okay? So it's not too far from 300. So this is basically the assumptions I'm making about the rooms where we are right now. So let's try to find the pressure. Okay, so this is how the room looked like. If your room looks any different, it actually looks like this, so it doesn't matter. Of length L, width L, and height L. So I'm going to make a lot of simplifications in here, okay? I'm assuming that the room is kind of a cube in this case, okay? So, and it's filled with these tiny particles. And they're moving every which way. They're moving in random motion. Oh, another assumption, which is very, very important. I'm going to assume that this room, this gas is isotropic, meaning there is no preferred direction for the air. The air not all of a sudden decides to move this way. No, it's going every which way, okay? Any direction you choose is similar to any other direction you could choose, okay? So this is a critical piece of information, that the motions are random and any direction you choose is similar to any other direction, okay? So isotropic, meaning symmetry in all directions. So don't tell me if you choose the x-axis that Maybe the y-axis would be different or the z-axis may be different. No, it's the same thing. Whatever you find in the x-axis is the same thing happening in the y-axis, is the same thing happening in the z-axis because of this assumption, which is a critical assumption. So these particles are moving every which way. I'm going to focus on one direction, as I was saying. I'm going to call this direction the x direction, the x-axis. Forget about the y and the z-axis for right now. They are irrelevant. And whatever I find in the x direction, I'm going to assume is the same thing as happening in the y direction and the same thing is happening in the z direction. So if I take a wall, this one, side of the room, so this side, a particle that comes in this way, for example, hits it at an angle and then bounces off in this direction. So this particle has a mass m, has a velocity, m, has a velocity v, it's really an of index I. What I'm assuming that there are n particles in here. There are n particles. Remember, Avogadro's number Na is 6.022 times 10 to the power 23. This could be slightly more than this number, slightly less than this number. If I have an Avogadro number, I have exactly this many particles. If n is equal to 1, the number of moles is exactly 1, then I have this many particles. If n is equal to 1.5, then multiply this by 1.5. If n is equal to half a mole, then it's 3 times 10 to the power. So it's a huge number. So the number of particles is a big number, okay? As long as I'm dealing with the order of a mole. Even if I am dealing with 100th of a mole, it's still of the order of 10 to the power 21. So it's still a huge number. So that justifies statistics. Statistics. This branch of science is called actually statistical physics. That's basically what the whole debate is. So I'm going to take a particle of index I. Remember, I is going to be summed from 1 all the way to n. There is no calculator that's going to sum 10 to the power 23. Not enough computer to do that. So really, it's a game of averages then. Okay, so that's the whole debate in here. The whole point in here is at some point we're going to take averages into account. Okay, so this velocity has components obviously in the x direction, has components in the y direction, has components in the z direction. What matters for me, since I'm focused only on the x direction, is the change in the velocity when it hits the wall in the x direction only, because the y direction, this component, if it's just going on the xy plane, is going to remain the same. So the particle is going down, it's still going down, okay? But in the x direction, the momentum was mvi of x. Now it changed to negative mvi of x. It moved in the opposite direction. So it was coming to the wall. Now it left the wall with this component of velocity. Okay. You're wondering what happened to the y component. The y component will happen the same thing when it hits the wall in the bottom. Or when the z component when it hits the wall on the side, if it tilts this way. So that's why I'm focused only on one direction, namely the x direction. And once whatever argument I build on that, then I'm in good shape. Then I'm going to say that the same thing is happening in the y direction and the same thing is happening in the z direction. Are you guys so far so good with me?
Yes.
Yeah.
Yes.
So all I am saying right now is the change in momentum. Actually, since this is a positive direction, so really I have to take this one positive and this one negative. This one was moving in the negative direction and this one is moving in the positive direction. So the change in momentum, I'm going to write the big P in here for the momentum to be the final value, which is mvi in the x direction minus the initial value, which was negative to begin with, mvi in the x direction. The quantity v is the same for two reasons. These masses are so tiny, these particles are so tiny that the wall does not budge, the wall does not move. Okay, and because this collision is elastic, the final momentum in magnitude must be equal to the initial momentum in magnitude. Therefore, in this case, and the kinetic energy is the same thing. So the velocities must be equal in magnitude, okay? Because there is no velocity for the wall, it's not going to move. So the change in momentum is going to be just 2mvix, okay? Because the collisions are elastic. When I say collisions, I mean two kinds of collisions. Collisions with the sides of with the walls basically of the room, and also between the particles themselves when they collide, that they have to all be elastic collisions, okay? That means that there is no loss of energy to friction or heat or any other phenomenon that you might think of. So that's it. So this is the impulse. Impulse imparted to the wall. This is from what you have seen in physics 1. Okay? The change in momentum is the impulse. The final momentum minus the initial momentum. Remember, this is one particle. Okay? What's happening in the x direction? I'm going to drop this symbol quickly and you will see why. This index I. Okay? Before I do that, let me. The argument you have in the book is kind of odd argument. It works. It's going to give us the correct answer. But technically, there is a better argument for it. So I'm going to follow the book for right now. And then later on, probably down the road, we'll talk about the better argument for the following, for it's going to come next. This is one particle. Remember, this is not the whole story. I have still this many particles of the order of this number. Okay, so this is Avogadro's number. So I really have to sum up through all of them to see how much really momentum was imparted to the wall from all of these ones that are hitting it in the x direction. So the ones that are coming in the y direction, forget about them. We're just focused on the ones that hit it in the x direction because this wall happened to be perpendicular to the x-axis. So let's consider the following scenario. I'm going to take the same side of the wall. I'm going to consider a cylinder of cross-section A, where A is a made-up surface. Particles are going to come on average in this direction with the velocity vi in the x direction. On average, about half of them are moving in the opposite direction. So on half, half of them are moving this way, about half are moving the other way. Because again, there is no preferred direction. It's an isotropic system, meaning that any direction is as good as any other direction. So about half of them are moving toward the wall, about the other half are moving away from the wall. So if we consider an amount of time delta t, this number of particles that are going to hit it straight on with this component, of course, of the velocity. So how many particles are contained in this volume at a given amount delta t? At an interval of delta t, in incoming number of particles. Okay, remember I have n particles in the entire volume. So this is the density of particles in the room. Okay, this is how many particles if I take a tiny volume of whatever dimensions are. I'm assuming it's uniform distribution, okay? Again, symmetry, okay? Since I'm taking a volume of cross-section A in length VI delta X, this is the length of that cylinder, then I have the volume, which is VI in the X direction times delta T. This is the length times the area A. This gives me the volume, but only half of them are moving this way. Only half of them are moving that way. This is the actual volume times the number of particles per unit volume. So this is the actual number of particles about to impact the wall in the next that the amount of time this many particles will hit it in this section only of cross section A. Did you guys follow the argument?
Yeah, it makes sense.
Very good. So basically all I took was the volume of how many particles are in here. I know how many particles are entire volume of space. They're n. N divided by V give me how many particles I have per unit volume. But I don't have really unit volume. I have this many volume, which is the cross section times the length of the volume. But I'm thinking half of them only are going this way. The other half are moving in the opposite direction. So the only half that is going to impact them is this many times, of course, the number per unit volume. So this gives me the number of particles that are going to hit it in this amount of delta T. Each and every one of them is going to impart this momentum, this impulse. Each particle is going to give it this much impulse. So the change in momentum for the entire wall. So I really should index this one with an I, honestly, because this is only with one particle giving it just this momentum, this impulse. So I really want to find the total momentum. I have to take all of these particles. I mean, let me remove that index I. Of all particles to hit it in amount in the area A first. So this is how much moment. So their number, first of all, is n over v times n over v, I'm sorry, times 1/2 times the area, which is vi x delta t times the area. This is the volume of these particles. This is their number per unit volume, n over v, times each and every one of them is going to give it 2 mvi in the x direction. Of course, vi and the vix is the same amount. The 2 cancels the 2. And the entire momentum now for all of that particles in that area is going to be equal to delta p is going to be equal to n over v times m times vix squared times delta t times a. From physics 1, if you guys remember, the force is just simply equal to the rate at which the momentum changes with time when delta t goes to 0. So it's the limit of this expression. So all I'm going to do is take this and divide it by delta t. The delta t cancels. I considered a finite amount of time delta t when this is happening. Now I'm going to take that delta t to go to 0. So that's going to be giving me the force exerted on the wall across the section A. So that force is going to be n over v times mvi x squared. Of course, I'm going to suppose to sum through all of this quantity in here. I'm summing throughout this quantity in here, okay, and multiplying by the cross-section A. I forgot to do that in here because remember I said that this is the throughout this cross-section. So technically, there is a term in here that I have to be careful with, and this is this VI in here, okay? I'm sorry, forget about this sum for right now. And that is because some of them are moving faster than others. I'm going to consider the following. I'm going to consider Vx squared to be just the average of these quantities. Okay. So I'm going to consider this one the average velocity in the x direction. Okay. So I drop this index I. So I'm going to take the average and drop the, so this force then becomes N over V times M times this velocity. Sorry, there is no index I anymore. The average velocity in the x in the x direction times A. But this is not the average velocity squared. This is the average of the square of the velocities. It has a name. It has a name, and that name is called the RMS. Okay, so this is the average of the square of the velocities in the x direction. Watch for the last statement in here, it's very important. Squared. So after you find the average of the square of these velocities, you square the quantity again. Okay, times A. The final thing that I want to do in here is the pressure P is the force divided by area. And this is where the area now doesn't matter. I took an arbitrary area, a made up area of cross-section A. And that cross-section is arbitrary. We could have taken it small, big, doesn't matter. At the end, what matters is the pressure. So this is the pressure. Pressure is force over area. So that area cancels now from both sides, and I have this expression, N over V times mv squared in the x direction. Okay. So we found the pressure on one side of the wall. This pressure must be the same quantity everywhere because the pressure is force divided by area, and the force divided by area should be the same everywhere because again, the area now doesn't matter. So the pressure in the in any direction is the same quantity now. I have to get rid of this x index. Let me show you how that works, okay? Remember, the velocity of any particle is given by the square root of the x component plus the y component plus the z component. Okay? Or if you wish, v squared is equal to vx squared plus vy squared plus vz squared. If I average this quantity, it's the same thing as average in here, the average is in here, and the average is in here. So this is the average of the squares again. Okay? Because of the symmetry, this average must be equal to this average, must be equal to this average. In other words, on average, the component in the y direction and the component in the x direction and the component in the z direction, they are all the same quantity because we're doing the average now. So on average, it doesn't matter which direction you're taking. Whatever you see the average is happening in the x direction is the same average happening in the y direction, is the same average happening in the z direction. Again, because there is no preferred direction. A given particle may be moving faster in one direction than the other. But there will be another one that is moving faster in the other direction than this one. So at the end, when you do the averages, the quantities will be the same. But I'm averaging the squares. I'm not averaging the quantities themselves. So what this says then this average is equal to Vx squared. This average is equal to Vx squared. That means that Vx squared, on average, is just 1/3 of the actual velocity, the average of the actual velocity itself, vector. So you take the vector, you square it, you find its average, you take it by 1/3. It's the same quantity in the x direction, the same quantity in the y direction, the same quantity in the z direction. So that's where the third comes in from. It's the fact that any of this direction is as good as any other. So when you square them and you average them, you're going to find the same quantity. So this is equal to Vx squared. This is equal to Vx squared. So you have 3Vx squared is equal to V squared, which means that Vx squared is just 1/3 of V squared. Which brings me to the final expression in here in terms of the actual velocity, not of the specific direction x or y or z, because we took x as just any other direction. So at the end, the pressure P, I usually write it lowercase p, okay, is equal to n over v, just to talk about that pressure, times 1/3 the mass times the average velocity squared. Okay, where now I don't have to deal with the x direction or y direction or z. I'm dealing with the actual velocity itself as a magnitude of the vector v. Remember, v has components in the x direction, y direction, and z direction, but it also has a magnitude and direction. This is its magnitude. This is this quantity, except that I'm finding the average of the square. Okay, so actually this expression in the square root has a name. It's called VRMS. That means you square the quantity. Here it is squared. You find it's the mean of the square. Here is the mean. And then you take the root of that quantity. So RMS stands for root mean square. Okay, you square the quantity, so you start the operations backward. You square the quantity, you find its mean, here is the mean, and then you root it. And at the end, this expression then becomes n over v times 1/3 of m times VRMS squared. Because that's the same thing. Have you seen the discussion on the RMS before? I'm sure you did before you did. Because
Yeah,
when you
it
did
was in our last class.
Yes, physics 2, you did when you did the voltage, and for the power, you had to deal with the RMS there, okay? So the root mean square is something that you deal with in statistics, because when you're dealing with squares, and in here, the square came in naturally. The square came in the product of two quantities that emerged from this argument and the previous argument for the momentum, so you dealt with the square. So now it's a quantity that is squared. And because this thing is related to the kinetic energy, therefore I know that this is somehow related to the square of that quantity. The final form I want to write this expression is PV equals to n, where n is this number, times 2/3 times 1/2 mv RMS squared.
We can't see it.
I'm sorry, I'm not sharing. So this is what I wrote. I took V to the other side, and I wrote PV equals to N. Instead of 1/3 by itself, I multiplied it by 2 and divided by half, because I know that this is somehow the average of the kinetic energy of translation. So if I average the kinetic energy, I'm going to find that quantity per molecule, because this M is the mass of the molecules themselves. So here is a law that I know from experiment. It says PV equals to nRT. Here is something that we just argued for based on our model for the ideal gas, based on our assumptions. Okay, the average of the kinetic energy of translation per molecule. Okay. It seems like we are almost in good shape. Not quite right, but we are almost in good shape, okay? If I'm going to make the following argument, N, the number of moles, is actually the number of particles divided by Avogadro's number. Then the first law can be written as PV is equal to N times R divided by Avogadro's number times T. So this one can be written as such here. All you have to do is just replace the value of the number of moles by the number of the actual particles divided by Avogadro's number. Now, this quantity R over NA, I'm going to give it a name now. K, I'm going to call it KB, okay? I know the book calls it K, and I'm going to call it KB because you will see different Ks throughout the class, especially the angular momentum. I mean, not the angular momentum, the wave number. So at this point, I'm just going to address it with the letter B in here, okay? So a lot of textbooks also use the letter B. Sometimes they don't, okay? So is equal to, by definition, R over NA. Remember, R is 8.13314 joules per Kelvin per mole. But mole is just a number, so I'm going to drop the number of moles right now for a second, okay? And I'm going to start with something else. R, if you wish, per mole, okay? This Avogadro's number is 6.022 times 10 to the power 23. Molecules in general, with an E in here, I'm going to add to it per mole. Cancel the mole for the mole if you like. And then this becomes per molecule. That's it. Okay. So everything else is the same, except that this number, 8.314 divided by 6, this number is equal to 1.38 times 10 to the power negative 23 joules per Kelvin. And again, in here, molecule. Okay. Just to make a distinction between this. Again, it's a number, okay? The number of molecules or number of moles is just a number, okay? Except in here, I know that this number is big, it's huge. So this power somehow is going to get out of the way. That's all. And this number is a finite number. Tiny n is a finite number. It's like 1 or 2 or 7 or 2.1 or 0.17 or something, okay? It's a number of with no powers, basically. Most of the time is a small number, okay? So that's the only distinction between these two numbers, but they are numbers nonetheless, okay? So I'm putting them in there as if they are units, but they are not units, just to make a distinction between these two. So this is known as Boltzmann constant. It was not Boltzmann who actually wrote it this way. It was actually the first one who did it was Mr. Planck. And later on in one of the papers, I forgot who's published it in the 1900s, it was actually referred to as Boltzmann constant. From that point on, people referred to as Boltzmann constant. And they didn't want to call it Planck's constant because Planck's constant is actually another constant, okay? It's another number. And we're going to deal with that Planck's constant down the road. So this is Boltzmann constant. So if I write it this way, let me reorganize this equation that we just found with this equation that we know from experiment into the one next to one another. So the one that we found can be written as follows. P times V is equal to N, the number of particles actually, times 2/3 times the average of the kinetic energy of translation in this case, and in this old law that is discovered by a bunch of people working on it, it gives me N times KB, where this KB is this tiny number, times the temperature T. This is the same PV. It would be nice if I divide the two, and from here, I have, if you wish, a definition of what that temperature is. From this expression, the temperature looks like it's 3/2 times the rate of the kinetic energy the average of the kinetic energy per particle divided by this KB, this constant, that's all. This is a constant, okay? This is just a constant. Or if you wish, you can leave that constant on the other side, KB times T, it's equals to 3/2 times the average of the kinetic energy, in this case of translation. Oh, did I add, yeah, that's correct. Everything is correct. Everything is beautiful. Okay. So this is a constant. It happened to be 1.38 10 to the negative 23, but that's just a constant. Okay. And this is the temperature that your chapter 17 dealt with. This is what you feel as cold when you touch a cup, or what you feel is warm when you touch something else. Okay. It's nothing but the average velocity with which the particles are moving every which way. Okay. That's basically in a nutshell what this expression is. So this is a very, very important result to explain what temperature is. So what is temperature? It's related to the kinetic energy of the particles as they move in the gas. Okay. Here is another argument in here, and we're going to come back to this expression, but let me just make this point in here because it's going to take me to the equipartition theorem, which we're going to use later on. The reason why I have a 3 in here, remember that where 3 came from? It came from the components of the vector v that I argued earlier. The vector v has 3 components in the x direction, y direction, and z direction, and that's what third it came from. And that 3 came about back in here, in this form in here. So if somehow I restrain my particles and fix them to move only in a plane, there will be a 2 there. There will not be 3. So the kinetic energy, if somehow is restrained so that the particles can move only in the xy plane, this is the number of particles in there. So each component of the velocity brings 1. Each component did I have the expression correct in here? Yeah, everything is correct in here. Yeah. So each component brings this 1/2. You know what? I really don't want to give you the yeah, I made a mistake in here. It's equal. Hopefully you guys caught it. KBT is equal to 2/3, not 1/3 in here. This is wrong. It's 2/3. This is wrong. 2/3. Did you guys catch it? Fix it, please, okay? If I take the ratio of these two quantities, it's going to be KBT is equal to 2/3 of KE, not 3/2. Did you guys catch the error?
Yeah.
Okay, very good. Sorry about that. I know it's wrong because it's going to lead to a nonsense quickly in here, okay? So the kinetic energy is the one that is, if you wish, 3/2 of KBT. So each degree of freedom, we call them degrees of freedom, okay, because you have 3 ways for the velocity to change in the x direction, y direction, the z direction. Each degree brings 1/2 of KBT. Because you have 3 of them, you brought 3 of them. Okay? And this is true, for example, for argon or helium. These are atoms, these are molecules of a single atom. So they can only move in the x direction, y direction, and z direction. Therefore, they only have 3 components in their kinetic energy. However, if I take, for example, an oxygen molecule, this is O2 or N2. They can go in the x direction, Y direction, Z direction, if you like, but they also can spin around or spin around. So there are actually 5 degrees of freedom, and this expression should be, when we take the expression correctly, each kind of kinetic energy, because this is a kinetic energy of rotation and the other one is a kinetic energy of rotation. In other words, if this is the O2 molecule, I can spin it this way or I can spin it this way. This spin around its axis has a moment of inertia that is practically 0. So it's not going to result in any kinetic energy in this direction, but it's going to result in a kinetic energy in this direction. It's going to result in a kinetic energy. That's why there are 2 additional degrees of freedom for this molecule. Okay. If I take, for example, CO2, well, CO2 is another story. CO2, depending on the configuration, actually, I could have a lot of degrees of freedom in here. I could have potentially also the vibrations. And this too will involve the vibrations too. And this number has to change. Although these vibrations are quantum mechanical in nature, and the problem gets complicated. So this number in here that you saw immediately come about this theory is because of our simplistic model that we're assuming only motion in this 3 directions only, and that's where the 3 came about. So if we really are talking about a diatomic atom, like for example air, which is N2 and O2, we're not going to find 3 over 2. We're going to find over 5 over 2. Okay. And if we take a polyatomic gas or a solid for that matter, the expression in here will be different. As a matter of fact, for a solid, it's going to be 6 over 2, which is 6 kBT. Okay. So you have to be careful in here with this model, how much you can take it and use it for. Okay. So this is, we're going to come back to it. I promise. To be continued when we talk about the molar specific heat. How are we doing on time? We still have about at least 15-20 minutes to finish to introduce the important topic, because I talked about averages. Okay. I know some molecules are moving faster than others. Okay. Some others are moving twice as fast, some others are moving slower, and so on and so forth. It's worth, first of all, to find this RMS, the velocity. So let's find this RMS in here. Remember, what is the expression here that we found at the end? The half of mass, half of m times v RMS squared. This is what I meant by the average of the kinetic energy. By this expression is equal to 3/2 of kBT. Half cancel with half. And from here, we're going to find V RMS equal to the square root of 3 kBT over m. We talk too much about these things. Air, let's look at this room in here. Room right now, it's 300 Kelvin. I'm going to assume it's roughly 300 Kelvin. And as the day progresses, so the temperature is going to be fine. KB, I just found the value of KB. It's 1.38 times 10 to the negative 23 joules divided by Kelvin. Remember, a joule, again, I made a big fuss over this number in here. It's nothing but kilogram meter squared per second squared divided by Kelvin, okay? The reason why I want to emphasize this point in here, because I have a joule, which is a kilogram meter squared per second squared in here, divided by Kelvin. The Kelvin cancel the Kelvin, so we're good. I still have a kilogram divided by a kilogram that cancel each other, and I will have a square root of meter squared per second squared. So indeed, this is the proper units. This has units of a square root of meter squared per second squared. So it's going to be a velocity for sure. Okay. So for nitrogen, which is really the main component of the air, okay, 78% is nitrogen, has 14 nucleons, okay, on average. And each one of them, the mass of the proton is 1.67 times 10 to the negative, 27 kilogram. So this is the mass of a given nitrogen molecule, nitrogen atom. Don't forget that I have two of them for N2. So this is an atom, not the molecule. So the molecule, the mass of the molecule is 2 times this atomic mass. So it's going to be 28 times 1.67 times 10 to the negative 27 kilograms. So we're in good shape now. We can find how fast this thing are moving around on average, okay? Or the RMS, the root mean square of their velocity. So V RMS of nitrogen in this room is roughly about the square root of 3. That 3 is part of the formula, times KB, which is 1.38 times 10 to the negative 23, times the temperature. The temperature is 300 Kelvin, divided by 28 times 1.67 times 10 to the negative 27 kilogram. Remember, the units are going to work out themselves properly to meter per second because everything is in SI. So I don't have to worry about that. Let me pull Mathematica and let me open a new book. Come on. I cannot even do that. Okay. And let me do this number in here. Let me first of all. This is something that you expected to do easily, okay? You can do it with a calculator. So let me stop sharing. Let me leave this screen in here so that you can see it. And let me share with you this notebook. So I want to find the velocity, so it's a numerical number. So n of the square root function of 3 times 1.38. I don't know how to do the exponents, so the only way I can do it is 10 to the power, open parentheses, of negative 23 times 300 divided by, open parentheses, 28. That's the mass of the nitrogen molecule, times 1.67 times 10 to the power, open parentheses, negative 27. I did everything correctly. And let's put 0. Can it give me like this or not? Did I do a mistake somewhere? Oh, I forgot to close the whole thing. That's why there was an error. Forgot to close the square root. Okay, it's telling me 515 meters per second. Did anybody find the answer to the roughly that number?
I'm actually inputting it as well right now.
Yeah, please. Can you guys do it to make sure that I didn't do a mistake in here? Because I do a lot of mistakes. I mean, this is no secret. Gabriel, did he say something? Because I can't hear you. Let me share with you again the numbers so that we guys are on the same thing. Somebody chatted in here. Okay, no problem. I can tell you the order of magnitude is correct, but maybe the number is a little bit off. Come on, guys. This square root and this square root cancel, so I have 10 to the negative 4 in here. Sorry?
I did it. I got the 515, the same one you got.
Very good, very good. Thank you, Joseph, too. Okay, so here is a problem with this number. The speed of sound it's about 340 meters per second. So what you're telling me then, if we did it for the oxygen molecule, this number changes to 32. That's all. So it's going to be slightly less because you're dividing by something here. Okay. Because O2, you have 16 times 2. Basically, it's the same numbers everywhere. So you're telling me now that this air right now is beaming with particles that are moving faster than the speed of sound every which way. So they should be blasting this screen in here and knocking everything every which way. And I don't see that. I mean, nothing. I mean, I had this in here, sitting in here for quite some time now. It did not get knocked off one way or the other. So what's going on? This is the number one criticism that Mr. Clausius, when he was making these arguments, basically, he didn't have all of this mathematics. It's actually Mr. Maxwell who put it together at the, before him, I mean, after him, that he faced, and he found to be a valid argument. This speed is too fast. I mean, I didn't do it for the hydrogen gas, for the hydrogen gas, by the way, H2. The mass in here for H2 is going to be 2 times 1.67 times 10 to the negative 27. So this number is actually 2 here, not 28. And you know, when you divide by a number, it's going to be higher. So the hydrogen will move even faster than this. And there are some remnants of hydrogen in the air. So the lighter particles will move faster. The heavier ones will move slower, but it's still nonetheless moving super fast compared to the speed of sound, which is 340 meters per second. So this criticism was this theory faced, and a lot of people made basically fun of it and started to call these people like crazy. I mean, they're coming up with some nonsense stuff in here. And this, Mr. Clausius himself admitted that this is a major flaw in the argument in here that we just made, and we needed to fix it. To fix that, Mr. Maxwell introduced the mean free path, okay, and mean free time. Let me go through these two arguments. We're going to close it for today. Thursday, when we meet, we're going to come up with a distribution, because not all particles are that's the other thing. Not all of the nitrogen atoms are moving with this speed. Some of them are moving slower, others are actually moving faster. Okay, so if you argue on one side, hey, they are slower than this, so don't worry about it, but there are some that are moving faster. This is just a mean. Okay, so we need to find a better way of describing the whole particles, or how they are zooming in and out of the room in here. Okay, so to solve this problem, as I was saying about the sound, the mean free path was introduced with the mean free time. So let's talk about it. Imagine each molecule has a radius r. So this is a molecule, radius r, okay? And it's moving in its path. If it does not encounter any molecule in this volume, it's in good shape. As a matter of fact, there will be another molecule of a similar size r within this space. As it's moving, if you don't encounter any particles, it's not going to scratch it, it's not going to hit it. Okay, so you're right, it's moving with this speed at that point. So we need to know how long or how frequent are this molecule collisions. that's the question. Okay, if they're extremely rarely, that in other words, that as it moves, it's going to hit one, it's going to hit another, it's going to hit another, then in this case, I don't have to worry about them hitting anything, because on average, first of all, they're canceling each other, and they're not coming anywhere from hitting my the thing that was sitting on this container here. So everything is fine. So that's really the whole argument behind it. So I'm going to assume that they have a finite size of radius r, and as long as one of them does not encounter any particle in here, it is still moving with this average speeds and so on and so forth. Okay. It resembles the argument you made for the conductivity of electricity in physics too. Similar argument in a sense. So I'm going to assume the following, okay, for this simplification, because we really don't have a full grasp of the statistical mechanics to do this. So I'm going to assume that all molecules are frozen. Except one. So this one that is moving, the others that are stationary, if it encounters any one of them within this volume of radius 2r, diameter of the molecule itself. Because remember, even if it brushes another one, that's a collision. If it comes on head-on, that's a collision. So anywhere in between on this, where there are two of them sitting next to one another, in other words, this is 2r and 2r, that's a 4r actually, you have collision, okay? So you want to find how often this thing happens. This is moving with an average velocity again of v, okay, which is the RMS value that we're talking about in here. I'm going to drop the RMS for a moment in here. Later on, we're going to restore it, especially when we come to the statistics of all of these particles. So during an amount delta t, similar to the argument before, it's going to move through this entire space, through this entire volume, and the volume is the length times the area, and the area has a radius of 2r. Remember, this is a circle of radius 2r, so the area is pi times the radius squared. The radius is 2r, not r, okay? So in this case, this is 4 pi r squared. So this is the number, as long, this is the volume it's going to encounter in this amount delta t. Well, there are a number of particles per unit volume, if you guys remember my initial argument of n over v. So this is the number of particles that it's going to encounter in this amount delta t. So in delta t, there are delta n collisions that is equal, so that the delta n is equal to this number basically, because I just counted how many molecules are exist in that one, because this is the volume and this is the density of the particles. So this is the number of particles that exist in that volume, okay? So basically what I'm saying in here is take n over v, multiply it by this volume, which happened to be v times delta t. Oh man, this v is different than the other v. This is the volume v, and this is the velocity. So I'm going to address it with a little bit of different in here. So this is the velocity, okay? So not only the p was a problem for the momentum and the pressure, but we also have this one. We have about 5 minutes to finish, I guess, the class. So I'm going to go a little bit quick in here. Times delta t, this is the length of the cylinder, times the area, which is 4 pi r squared. This looks like an area of a sphere. This is not an area of a sphere. It's an area of a circle of radius 2r, okay? From here, I'm going to find the rate of these collisions. The rate of collisions which is delta n over delta t, is simply going to be n over v times v, the velocity, times 4 pi r squared. Okay, here is a word of caution in here. This argument assumed that all of the particles were stationary. This is not true, okay? They are all moving actually, including the one that we were focused on. So this actually increases the rate by a factor of square root of 2. Proper inclusion of motion of all molecules using statistics, which is really a little bit outside of the scope of this course, introduces square root of 2. In other words, this rate increases by a factor of square root of 2. So the actual formula now is delta n, the rate of collisions, delta n over delta t, is simply equal to n over v. Remember, n over v is still given by that PV equal to nRT. So we can still find the volume using the relationship PV equal to nRT or n kBT. So we still have n over v equal to p over nkb, nkbt. So we still have that expression here. Times that square root of 2, just as that made the argument for it with the proper treatment of this expression. So it's going to be 4 square root of 2 pi r squared times v, where v is the velocity here. This is a number of collisions per second. Per second. If we do the calculation, it's going to be very high collision rate. So it's not going to do that, that damage that I was thinking that might happen. As a matter of fact, I'm going to define tau, the mean free time, as just being the inverse of this number, which is v over n times 4 times square root of 2 times r squared times v. Okay, where the v is that velocity, the RMS velocity that we were talking about earlier. Okay, so this will give me collisions every fraction of a nanosecond. So particles really hardly move without doing any calculations. If I plug in the numbers for a typical gas in here. Meanwhile, I can also find the mean free path. I think the book uses the letter L. Books usually they use the letter lambda for it. It looks like it's a wave number. It's not. It's a mean free path. Meaning, how long does it take to go for this one without collision? It's just the velocity v times tau. If I multiply v times tau, the v cancels from the numerator and the denominator, and this expression will become, sorry, v, not n, the volume over n times 4 times square root of 2 times pi times r squared, which is the radius of the molecule itself. Typical molecules have an r of the order of 1 angstrom, or 10 to the negative 10 meters, because half an angstrom is basically the size of the hydrogen atom. Hydrogen atom, put it next to a hydrogen atom, and now you have half and a half. That's about 1 angstrom, which is 10 to the negative 10 meters. So that's the typical size of the molecules. Maybe slightly more, maybe R is equal to 2 for a case of a big molecules, huge ones, but typically it's 1 or 2 times 10 to the power negative 10 meters. This unit 10 to the negative 10 has a name in here. Okay, we still have about 2 minutes, but I think we're in good shape in here. We introduced a lot of concepts today. Okay, we still have to do a little bit more statistics down the road on Thursday. We're going to introduce Maxwell Boltzmann distribution, and we're going to do the Gaussian then, and we're going to do several examples from this chapter. Sounds good?
Yes.
Yeah.
Very good. So thank you, guys. If you have any questions, please do send them. There will be no discussion item today, but there will be Thursday discussion items, especially for doing the Gaussians and things like that. Sounds good?
Yes. Yep. Have a good one.
Yeah.
Professor.
Okay. See you guys Thursday, same time.
See you, Professor.
Thank you, guys.
Bye. Thank you.
Thank you, guys.